Looking at our keywords, we started to look at different types of schedulers. Can you spot the different types of schedulers on the keyword wall? Today we're going to be looking at the different types of operating systems. This includes distributed, embedded, multitasking, multi-user and real-time operating systems. Try to answer the questions and then look at the answers. Did you get them correct? Here are the 5 different types of operating systems. First of all, we're looking at multitasking. On modern computers, we know that we can have more than one application running at a time, such as listening to music, with a Word document open doing your homework, and emails in the corner. When we have one processor, each processor is given a small slice of time, so it appears that they're running simultaneously. Remember, we looked at scheduling last week, and this showed us how we could split up the different processing time evenly between different processors. If we click Ctrl, Alt and Delete on our keyboard, we can actually see which processors are running. And you usually find these types of computers and operating systems on home computers. The second type of operating system is a multi-user. There's a couple of examples of this, such as we can have a single powerful mainframe computer or supercomputer with lots of other computers connected to it using its resources. Each of those computers would get a slice of the processing time, according to the different scheduling algorithms again. We can think of a school network as having multiple users with the same resources. We could have a server where all different users are having a time slice of that server. We can also think of an operating system having multiple users on one machine, where different users could be logged in. There are distributed operating systems, and this is a form of parallel processing, and it spreads the loads over multiple computer servers. So the job is split into several different tasks, each run on different computers, coordinated by the operating system. And to the user, though, it appears that the computer is running a single system. This is great for loads of power. It increases your power for very complex jobs, which mean that you need a lot of processing to actually get that job completed. NASA uses distributed operating systems. When they were mapping the stars, they recruited a series of volunteers who would leave their computers on at night, and the processors would process a tiny part of the map so they could create a map of the stars. You can also think of a supermarket when you think of a distributed system. If you're buying several products at the same time, your basket is going to have all the items that you've ordered, and they're going to stay on that server until you check out. Now, you might not be the only person with stuff in their baskets as well. But when you're searching the site, you might be searching a different server, which holds lists of all the different products available. This is a distributed server. However, to you, it looks like you have one system. We have previously looked at embedded systems, and we thought a lot about the features. We should know they have dedicated hardware, and they're designed for one purpose and to specialise in that one purpose. This might be a speed camera. It might also be a task within a larger system. You find them in household items such as washing machines, microwaves, but you also find them in aircraft, and each one has that specific task. They have a very simple user interface, usually a couple of buttons. They might have a command line interface. They're unlikely to have a very advanced user interface. They will accept input from buttons and sensors. They have limited RAM, and sometimes it's just instructions stored in ROM. Remember, they're RISC processors, and usually they don't have a permanent data store. We could potentially have Harvard architecture. when we're thinking about the structure of an embedded system. Remember, that has split memory. That means we could have RAM for the instructions, which is held separately to our RAM. They usually have low power and they're efficient. The final type is a real-time system. These are processors which need to execute data within a known time frame, and they need to respond instantly. Think about a Tesla driving along the road. If another car was to pull out in front of it, it needs to respond immediately, and we can't wait for that process to take its time to figure out what's going on. So we need real-time processing. So what we do is we build an element of redundancy into the system so that the processor never actually runs at capacity. That way, if something out of the ordinary happens or there's an increase in processing or input, we can handle that. We sometimes call these safety critical. You might see them in army systems when we're looking at missile systems. You might see them in insulin trackers for people with diabetes. They need to respond quickly to sensors or an input. And they need to be able to deal with simultaneous inputs, so several inputs at one go. They need to have a fail-safe design so that the components are not going to fail. And remember, they have redundancy. This means also if part of it fails, it can switch to the backup. Sometimes we get hybrid systems. If we think of the word hybrid, quite often we think of cars. A car that runs half on electricity and half on gas or fuel, so petrol. If we look at the definition, it's a combination of two elements. Think of dogs. You can interbreed dogs, so you get different types, like a cockapoo, a cocker spaniel, and a poodle. So a distributed system could actually have multi-users. A real-time fighter jet could have part of an embedded system, but it has to be in real time. So these hybrid systems could be more than one type of operating system. Please now try the exam questions that go with this unit of work.